Hello again, everybody. In this video, we're going to take a look at the vector class, the sort of like standard library vector class here, and pop the hood on it and see a little bit of like how it works here, because it has a little bit of magic in sort of what it can do. And while we're looking at, we're going to look at something called amortized analysis, which is sort of looking at like, not just what happens when you run a function once, but what happens when you run it sort of multiple times. For some functions, the sort of sum of running the function over and over and over is not necessarily what you would expect here. Like imagine we have a function with a best case runtime of O of 1, and a worst case runtime of O of n, and you run it in a loop. So you might expect that like, okay, what's the worst case runtime for the whole thing going to be? It's going to be n plus O of n plus blah, 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 blah. But that might not necessarily happen, right? Like if this O of n here does something that makes it so that like the best case happens more often, then you might not end up with a total of O of n squared. Okay, here, so we're going to take a look at the sort of standard library vector class here. And it's basically implements like an extensible array. It's like a normal array. It supports like O of 1 with subscripting there like that. But a vector can grow. Like the pushback operation adds new things onto the end of it. We've already seen that in the sort of string splitting like video there. So pushback is a little bit magical. Like this isn't something that normal arrays can do. In C++, a normal array, the size is fixed. If you create a dynamically allocated array, you specify the size. That's how big it is until you destroy it there. For a non-dynamically allocated array, like a statically allocated array, the size has to be a compile time constant. It's even more restrictive, and it still can't change here. So pushback adds a new element onto the end of the vector, and the C++ standard library guarantee that it runs in O1 best case time, ON worst case time, and then this new thing, O1 amortized time. What amortized time means is if you do a bunch of pushbacks, if you're doing like pushbacks in a loop, over that loop, the average runtime of each pushback will be O of 1, even though some of them will be O of n. Like a few of them will be O of n, but if you sort of add it all up and divide by the total number of pushbacks, it'll look like the average is. So how does that happen? Well, part of that is something we've already seen. So under the hood of a vector, right, it has both a size and a capacity. So the capacity is the actual size of the array, and then the size is how much of it we're using here. And whenever size is less than or equal to capacity, we can add a new element easily. You just put it like in the next available spot, and then we increment the size there like that. So we did that in the bag example, like just put it at the end and sort of add a new thing there. That's also how like the stack, the array-based stack code works. So we've sort of seen that already there. But with both the bag and the array-based stack, when size is equal to capacity, we're just full and we're done. You can't add any more stuff here. Vector doesn't have anything like that. So this is what our sort of vector class is going to look like here. So privately, we have an int pointer to our array. We're going to dynamically allocate an array. And then we have a couple of variables tracking our size and our capacity here. So in our constructor, we set our initial capacity to whatever. We set our initial size to 0, and then we dynamically allocate our array of that given capacity. We have an array of capacity 4 or 8 or whatever, but the size equals 0 says that we're not using any of it. And then in the pushback function, as long as the size is less than the capacity, things are easy. We just drop the new element into the next available spot and then increment our size here. So this over here should be pretty obviously O of 1 there like that. Like that's sort of nice and fast here. But we're incrementing size over and over, so eventually size is going to be equal to the capacity, and we're going to be quote unquote full. So what do we do then? What needs to happen here? So like a vector never fills up. It's never like, sorry, you can't add any more stuff. So something needs to happen over in the else part of this to give us more capacity. Now, like I was saying, right, this part, easy, O of 1, there like that. But what do we do down here? What do we do when we're full and the size is equal to the capacity? Again, remember, like normal arrays, there's no way to take a normal array and be like, hey, I want to increase the size of this array here. Once you create that data array in your constructor, the size of that array is fixed. So let's just sort of trace through the first few pushbacks here. So we're setting up an array not of cap 8, of cap 4. Sorry about that, like that right here. And initially our size is 0. So we'll do some pushbacks here. So if we push back 12, 12 goes there, size gets bumped up to 1. If we push back -4, right, so we're just doing these in order like this, right? The -4 goes there, and the size gets bumped up to 2. Push back a 2, it goes there. All right, size gets bumped up to 3. And then finally, do the final pushback of 7. 7 goes there, size gets bumped up to 4. Now what do we do? Right? Our array is full, but we don't want to sort of impose the restriction that like, well, now I guess you're stuck, sorry. So we have to figure out what to do here. So what a vector does is we're going to create a totally new array with a larger capacity, copy all of our stuff into it, and then we delete our original array and swap it out. So that's what we're doing over here. We're going to pick a new capacity as the current capacity plus some amount of stuff, and then we're going to create a new array of that new capacity there. Then we have to do a loop to copy everything from the current array into the new array. Once that copy is done, we can then delete the current array because we've got a copy of it. And then here we just swap out the new array and the new capacity. And now we have a new bigger array with more space available, so we can do the sort of pushback that we originally wanted to do here. Now notice that we've got a loop in here from 0 to size. Size is our n. So that means this is going to run in O of n time. All this other stuff here is O of 1. Right? This stuff up here is O of 1 like that. So this loop with the O of n is going to be the runtime for the else case here. So we now have two parts to our sort of pushback. O of 1 is our best case, and then that else part here runs in O of n time, and that is our worst case here. So our question is, if we do pushbacks in a loop that runs it n times, will the sort of total worst case runtime work out to O of n squared? And the answer is not necessarily, and that's because one of these bad O of n pushbacks can't immediately be followed by another one. Like you can't do an O of n pushback and then the very next pushback is another O of n. And that's because this O of n pushback that we did here gave us more room to do cheap pushbacks here. So we can't have this pattern here. We're just doing bad pushback after bad pushback after bad pushback here. Every bad pushback is followed by some number of cheap, easy pushbacks here. So the pattern that we have looks something like this, where it's like bad, right? And then some number of good ones. And then bad, and then some number of good ones. How many good ones we get depends on how much we add to the existing capacity. So when we pick the new capacity as the existing capacity plus something there, this thing over here determines how many good pushbacks we get after a slow pushback there. So it's not immediately obvious that if you just add all this up here and average it out, you will get like O of n. That it would be just the same as the worst case there, because I can't have worst case after worst case after worst case. Every worst case is followed by some number of best cases. So to determine the average here, what we're going to do is we're going to track through the first 13 pushbacks. If 13 seems a little bit weird, it's just because that's where kind of like the pattern becomes visible. So that's why I sort of picked that there. And we're going to look at the cost of those pushbacks here. We're assuming an initial size of 0 and an initial capacity of 1. And whenever we need to, we're going to increase the capacity by 4. Now, of course, plus 4 isn't very realistic, right? Like in the real world, we'd probably do like plus 100 or something like that. But I'm keeping it small so that like we can actually like see what's going on in here. The cost that we're tracking here is kind of in a like a stepwise analysis. We're basically counting operations that look like this. How many times do we put something into an array here? So this array, that could be either the original data array that we have, or it could be the new data array that we sort of create in the slow case there. So if we look back at our code here, right? So again, we're looking at things that look like this. We're counting those here. If we look back at our original code here, let me scroll back over here. This right here, right? Right, it's a little messy. So in here, we do that here inside of the loop, and then we do it down here outside of the loop. This loop runs n times. So in our worst case, our cost is going to be n plus 1. And then if we go up one more to our sort of easy case here, sorry, back up here like this, right? We do that operation here. So this has a cost of just 1. So those are where our sort of two costs come from for those things here. Our fast case has a cost of 1, and our slow case has a cost of n plus 1. Apologize for sort of skipping around there like that. Okay, so here's our table starting from sort of nothing here. So we start with a size of 0 and a capacity of 1. So our first pushback, right, size is less than capacity, so that's a cheap one, right? Our size gets bumped up to 1, and it has a cost of 1. All of the easy pushbacks have a cost of 1 there like that. But now my size is equal to my capacity. So that means my next pushback is going to be a slow one here. So this here, in this case, 1 is my n. So this is n plus 1, or it's just the new size. Like you can think of it like that right here. So this is one of our slow pushbacks here like that. It has a cost of 2 there. But that bought me some cheap pushbacks because 2 is less than 5. So 1 plus 4 gives me a new capacity of 5. But now I get a few more free pushbacks. I'm going to get a few more sort of cheap ones in this section right here. In fact, the next 3 pushbacks are all sort of free, right? So less than, less than, less than, there like that. Only when I get here are they equal again. So all of these here, those are all easy. But when we hit 5, again, like, 5 equals 5, we're going to have to do a slow pushback. So we're going to do 5 plus 4, new capacity of 9. And then my new size is going to be 6, and my cost is going to be 6. Like that right there. So now we have another slow one here. So at this point, you can kind of see the pattern, right? Is we have slow, and then 3 fast ones. So this slow one here is going to be followed by another 3 fast ones after that as well. Right, we can just sort of fill out the rest of it here. This is why I ended at 13, because that's where that sort of pattern ends kind of nicely here. So we've got sort of 3 copies of the pattern of slow, fast, 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 slow, fast, 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 slow, fast, fast, fast. So now what we're going to do is I'm going to group these together as the slow one together with the fast ones that it enables, and we'll look at the average cost per pushback for each group. If we do that, if we fill out the cost per pushback here, so in this group right here, our total cost is 2 plus 1, 2, 3. So our total cost is 5. And we did 4 pushbacks. So my average cost per pushback is 5 over 4, or 1.25. In the next group down here, right, my total cost is 6 plus 1 plus 1 plus 1, which is 9. I did 4 pushbacks, so it's over 4. So my average is 2.25. In the last group that we looked at down here, right, I did a total cost of 10 plus 1 plus 1, 13, but I did 4 pushbacks. So my average cost per pushback is 3.25 here. So my average cost per pushback is increasing. In fact, it's increasing linearly. We want that average cost to stay the same, but it's not. It's going up. So as the size increases, my average cost per pushback increases along with it here. So that means that like what we didn't work. Our average time is O of n, which is the same as our worst case time. It's actually something like O of n over 4, but big O don't care, right? Like big O doesn't care about like if you do it over a fraction or something like that. That counts the same as O of n here. And in fact, it should be sort of like pretty obvious that doing plus x for any constant x isn't gonna work. Like we tried x equals 4 and we got 5 over 4, 9 over 4, 13 over 4 there. If you do x equals 3, then you get 4 over 3, 7 over 3, 10 over 3 like that. If you do x equals 100, then that kind of spaces them out, right? You get 101 over 100, 201 over 100, 301 over 100. Increasing x spaces out the points at which we have to do the expensive pushbacks, but it does not affect the average. It's affecting like the denominator, right? So you have big O of n over 4, or you have big O of n over 3, or you have big O of n over 100. But in big O terms, those are all the same. Those are all still big O of n. So adding a constant isn't going to work. We want the average to be O of 1. So what we need is for those fractions that we're building up, cost over number of pushbacks to be constants. So we can't control the numerator. Like the growth of the numerator, that just increases as the size increases. The numerator is the cost, and the cost is how many like copies we had to make there. We need the denominator to grow at the same rate, and the value of x becomes the denominator. But why don't we just make x be the size? Remember that we're in the situation where the size is equal to the capacity here. So you could just do cap plus cap, or if you want to do, you could do cap plus sz. Both of those would do the same thing. Or of course, you could just do 2 times the cap. Whenever we need more capacity, we double the existing capacity. So now we're going to try that out and fill out the table for this. I won't work through it sort of line by line. I'll just sort of give it to you like ready to go here. So once again, I've got the expensive pushbacks, and then I'm grouping them together with the cheap pushbacks that they buy us here. So this expensive pushback of 2, that only buys me 1 pushback itself here. So my cost per that, my average cost per pushback is 2. In the next group, my total cost is 4, 3 plus 1, but I did 2 pushbacks. So 4 over 2 averages out to 2. In my next group, my total cost is 5 plus 1 plus 1 plus 1, that's 8. But I did 4 pushbacks. So that also has an average of 2, all the way sort of down here. So as my cost increases, the number of pushbacks that I get for that cost increases the same way as well there like that. So my average cost per pushback here is constant. And that lets me conclude that my average cost per pushback, my amortized runtime, is going to be O of 1 there. That's the trick that vectors use to get sort of amortized runtime O of 1 pushbacks, is they double their capacity there. Any constant would work, right? It has to be greater than 1, of course, they're like that, but any sort of constant multiple, as long as it increases the capacity by at least 1, will result in sort of amortized constant time. It just affects the denominator on the fraction there like that. If you use a value between 1 and 2, then the average cost per pushback goes up, but we're sort of wasting like less memory, right? We're not sort of like over allocating the memory that we need there. If you use values larger than like say 2 or 3 there like that, that will reduce the average cost of the pushback even less, but they'll waste more memory as we sort of go along there like that. I think that most standard library implementations use, like they double the size there. Maybe if I'm remembering correctly, like Visual Studio, C++ uses like 1.5, but I might be wrong about that. Now, a related thing that we might want to build here is, what if we want to build a double-ended vector where we can do both push back and push front? We want both of those to run in amortized O of 1 time there. So the way that we do that is kind of the same way that we do it for normal vectors. We're going to leave some unused space at both the beginning and the end. I have unused space beginning and also unused space at the end there. So if you want to do a push front, that's going to go there. And if you want to do a push back, it's going to go there. So my push front is just, okay, as long as the front isn't all the way at the very beginning, because then we'd sort of be up against the beginning of the array there like that. As long as the front is not equal to 0, we decrement the front, move it like that, and then just drop the value into the new front position. Push back should look pretty familiar, right? As long as my back is not all the way over there at the end, and there's no more room for me to do stuff here, I just increment my back and then drop the new element here. So I just sort of move like that right there. Both of these have, like, these are the sort of easy 01 cases, right? Right there. But then both of these have the else's where we're up against the end of the array. So what do we do there? Like, imagine we're in this situation here. In this case, back is over here at, excuse me, not 7, that should be 9. Forgot that I made this array of size 10 there like that, right? So I can't do any more pushbacks because then I would be going beyond the end of the array there like that. And obviously I don't want to do that. But on the other hand, just like we saw with like the sort of queue sort of structure here, this is no longer full. Like in a normal vector, when back is up against the end here, we're full and we have to allocate a new array. But here we have some available space that we could use. So when we sort of become full on one end, either the back or the front, we have two different options that we could do here. So we could do like a normal vector. We can just double the capacity and then copy everything over into the new array here. But we could also just keep the array we have and just do a loop to recenter the stuff within it. Like if we go back here, you can imagine a loop that just takes this stuff here, right, and just sort of moves it over into the middle of the array so that I have equal amounts of unused space on both the left and the right-hand sides there like that. Both of these are going to run in O of n time here. It's just that this second option here doesn't use any additional memory, whereas the first one does here. So the way that this is normally done is we're going to compute basically the ratio of size to capacity. So the size is just back minus front plus 1. Size over capacity, and we're going to call that alpha. That's the Greek letter alpha, but it just looks like the letter A there. If alpha is less than 0.5, then we're going to recenter without reallocating. So that means we're less than half really full there. We're not going to create a whole new array. We're just going to take what we have and put it back into the middle here. But if we're more than halfway full, we're going to reallocate and then recenter it in the new array there like that. If we sort of combine these two together here, that gives us O1 amortized time for both push back and also push front. That's how you would build a double-ended vector. Sometimes that's called a D vector, a DE vector. Sometimes it's called a deque, DEQUE there like that. Those are a couple of names for this data structure if you ever find yourself sort of needing that there. So those are a couple of examples of sort of amortized analysis. We'll see that later on because, like, we're looking at data structures. We're looking at sort of like classes. So a lot of times when you run a function on a class, it changes something inside the class, which means that when the next time you run that function, maybe it doesn't have the same runtime. Maybe it runs like faster or slower, depending on what previous runs did there. So that's a little bit of amortized analysis there. You can do amortized analysis in a like super formal mathematical way. I'm sure you could find some references for that there. We're not going to need any of the really formal mathematical stuff in this class, but if you take an advanced data structures class, they'll show you like the accounting method and the potential method are the sort of two mathematical techniques for doing amortized analysis. But that'll do it for now. So thanks a lot, everybody, for your time.